Yeah, so first of all, thanks for inviting me to this event. And it's very strange for me because, and also ironical, because the office where this event is happening, that's where I go every day. But today, because of some strange final minute, scheduling issues, I had to travel at this moment. So I'm right now at the airport in a cafe giving this talk. I hope not many people stare at me thinking what I'm doing here. The other problem I have, unfortunately, is I have to rush for my flight at 6:15. So I would love to take questions, but I have a hard stop at around 6:15. Yeah. So with that, let me begin the talk. So thanks, first of all, to Jenny for setting up the context very well. And in fact, I was very excited to see all the great work Toloka is doing in the area of low resource languages, and it's totally aligned with the work that I have been doing with my colleagues at Microsoft Research India, and more recently I have moved to a team called Microsoft Turing, which works on these large language models, things like GPT-4 plus Bing and stuff like that. The things that I'm going to share are more from what I did with my colleagues from MSR, and I'm still working on them, which are around low resource languages. So how can we scale these large language models for as many languages as we can? And actually, the second last question, which was about transfer. Can we transfer, or how well can we transfer from Niger Congo to, let's say, Indo-Aryan languages, or from Arabic to Korean? So across families or within families. This is exactly the question I'm trying to answer in the talk. But before that, of course, I'm not going to tell you a lot about the situation today. You all know about ChatGPT, GPT-4. They have taken the world by a storm. But one good thing I want to point out is, the fact that this technology at least is kind of available or known to the whole world. When I say available, I don't mean people can use it as much they want, but at least everybody know about it. There is some way to access it to some extent, and this happened very quickly. In a matter of just 5 days, millions of users could access ChatGPT. Now, this is a good sign. This is a very positive sign that technology in some sense is democratizing. But unfortunately, if we look at some other axis, the story is not so rosy. And one is that of language. This is a work we did a couple of years ago. We tried to estimate the amount of resources that's available in various languages of the world. There are 7,000 languages, and the two kinds of resources that are important, which Jenny also mentioned, one is unlabeled corpus, like running text, and one is labeled data, which requires human supervision. So, of course, labeled data is more expensive to build. Unlabeled data is slightly easier to get for some languages. So if you plot the world's languages in this, way, you will see that some languages have very large amount of resources and some has nothing. The interesting thing to note is this is a logarithmic scale on both sides. So this language, which has highest amount of resources, is English. And the next set of languages, which include languages like Chinese and Spanish, has one order of magnitude less resources than English. And that's exactly what, again, Genia was mentioning. So even though we call Chinese a high resource language, the gap is still huge from English. However, the gap is even huge if you consider the other languages. So looking at this distribution, we divided the languages into 6 classes. And, there are only 7 languages in class 5, the high resource languages as we call, and there are 2.5 billion speakers of these languages. Whereas, in class 0, where there is absolutely no resource, more than 2,000 languages are there and spoken by 1.2 billion speakers. So in some sense, 88% of the world's languages spoken by 1.2 billion speakers are completely untouched by the benefits of the language technology that we are building today. So that's something to keep in mind. So the technology that we are all very excited about today, that many of you were asking about, transfer, etc. This came around in 2019. So in short, what this technology does is, if you feed it a lot of corpus of different languages, so I take English, Hindi, French, Swahili, Kannada, everything separately and train a model, it learns somehow a common representation for all these languages. And after that, if I have, let's say, labeled data, which is difficult to get and for which you need, um, uh, startups like Toloka or crowdsourcing platforms. For that, you can get this kind of data, let's say sentiment analysis for only one language, let's say English. Now you train it with English. Now, ideally, this should definitely work for English, but quite surprisingly, it starts working for all of these languages. So this has a big promise, right? So the promise is, now with only unlabeled data, we can get fairly good accuracy across a large number of languages. No language specific label data is required. However, if you look at it a little more minutely, and many people have done this research, including ourselves. So if you look at tasks and accuracies of across tasks, across languages, there is a huge gap. So in this graph, there are a bunch of tasks that are shown on x-axis, and the accuracies across those tasks for languages from various families. And you see, English has the highest. The plus there is English. So it has the highest accuracy. The data was also in English. English is called the pivot language here because the original data using which the model, label data using which the model was trained, is in English. But for all the other languages, you can see there is a varied amount of accuracy, and some of the languages like these Sino-Tibetan languages, or sometimes these Austronesian languages like Indonesian, Santali, have very low accuracy when you start with English. So we need to do something for this. The solution that we are talking about is not a panacea, but it holds a lot of promise. So what can we do? So that's the question I'm trying to answer here. Now, many of you might say that this is paper from 2020. I'm talking of technology from 2019. World has changed dramatically since then. Yes, you are right. 3 months, in November came ChatGPT, and more recently in February or March, we announced GPT-4. These are much more powerful models. But even recently, my colleagues in MSR and Microsoft Africa Research Institute had done a benchmarking experiment, again similar to Genia, what she was talking about. So a systematic experiment with GPT 3.5, which is actually ChatGPT. And they showed that it's not better for low resource languages from actually some of the earlier generation models, like let's say Turing, TULR version 6, and so on. So it's not that we are really, we are making a great progress in language technology, but all languages are not moving equally. And in fact, if anything is happening, we are widening the gap between the languages which have and languages which don't. So the three things, the question is then, what can we do? And we can take a systematic approach here. And I would say there are three things that we should do. First is even to understand where we stand with respect to each language. So that comes with evaluate. And as I will say, even evaluation is a hard task. The second is, once we have evaluated, we need to ask questions like, what affects the transfer? So explain this zero-shot transfer. And if we understand that, if we can explain that, probably we can exploit our understanding to strategize the third step, strategize data collection, and strategize in other ways to help all languages come as close to the high resource languages as possible. So I'll go through all these three items one by one, but most of the time I will spend on evaluate, because the other two kind of follows immediately once you evaluate things properly. To start with, while you can get transfer learning without labeled data in a language, you cannot evaluate for a task without labeled data in a language. So evaluation demands labeled data in all languages. That's one thing to remember. And unfortunately, we don't have that. So this is a graph which shows how much data we have across languages for evaluation of simple tasks like sentiment, or natural language inferencing and so on, it turns out that there are some 60 or so languages where people have collected data out of 6,000, mind you. And even for those 60, out of those 60, it's only like the top 10 languages where you have sufficient number of tasks. For all the other languages, as you can see, there are 1 or 2 tasks. So it's almost like we have evaluated for 15, 16 languages, and we see transfer learning works, and we are claiming that, hey, it works for every language. It's like I have built a medicine which works for human and whale, and I claim it works for all mammals. A doctor will never do that, right? So as language technologists, we should also never say that. So ideally, we should start with a very solid evaluation. So for that, data collection is vital, and all that which Genia told before me applies. And there is no shortcut to that. However, what if we could, at least to some extent, predict the accuracy of a trained model in a particular language, given all the setup conditions? I'll come in a moment what do I mean by the setup. And if we can predict, there are, of course, one thing is I have at least some rough estimate of how well this model works in my language. But more than that, I can also use this predictor to understand what affects my cross-lingual transfer accuracy. Again, going back to the question asked in the previous talk. So I can understand that. And the second thing, it also might help me, exploit this understanding. So given a fixed budget of data collection, I might prioritize now in such a way that based on my prediction, I know that I will kind of optimize accuracy in certain languages which are of my interest. So for last 2-3 years, we worked on a project called Litmus, linguistically informed testing of multilingual systems. And we tried to solve this problem. It will be difficult to get into, given the short time, it will be difficult to get into the technical details of how Litmus works. At a high level, I can tell you that it's a regression that we learn. Each language is represented as a feature vector based on certain things that I will show you in a moment. And then you try to predict on new languages. But functionality-wise, this is what it does. You can select, so this is a demo of Litmus, which is available online. You can go and check. The link is here. There's the code also available. You can develop on top of it. Many people have been using it and developing on top of it. So what does Litmus support? To start with, you can specify which model, which pre-trained model or embedding you are interested in working on. Then you can specify what task you are interested in. Then you can specify how much data you have to do the fine-tuning. Fine-tuning requires labeled data. So you might say, oh, I have 1,500 examples in Tamil, and or maybe you can say I have 1,700 examples in Tamil and 1,700 examples in Japanese. So you can select whatever you want. So these are called fine-tuning configurations. So you give these configurations. Then you tell it what target languages you are interested in. So these are languages where you want to know the accuracy. So let's say I'm interested in knowing about the accuracy in English, French, German, Tamil, etc. So then you run the model and it gives you something like this. It will tell you, okay, for French, you will get this much accuracy, for German, this much. And it will also tell you the mean absolute error of this prediction is 0.4%. So for French, if it is predicting 92%, then it should not be, it should be between 91.6 and 92.4, but not the range should not be more than that. So it's that way, it's fairly good, right? If you can make predictions within 0.4%. Then you can do a next thing, which is even more useful. So there are these budget settings. You can say that, okay, now I can collect more examples, more training data. So it asks which languages can you collect training examples in. So I can say, okay, these are the languages. Then it asks how much additional examples can you collect. Okay, 8,000 additional examples. I can give it more detailed constraints like, language specific budgets, etc., etc. Then I can also tell it what I want to optimize. So I might want to optimize the average accuracy across all these languages, or I might want to optimize the average, maximize the average, subjected to certain constraint that no language should have less than this much accuracy. So I can do all sorts of sophisticated, planning here. And then when I run this system, it tells you, how much data you should collect in various languages. And then it also tells you if you do this collection, you will get 5.77% higher accuracy, than a baseline accuracy that you started with. And it also says that if you were randomly dividing your data collection, so you are interested in these 6 languages. So maybe you want to collect, 8,000 examples. So 8,000 by 6 in each, so equal amount. So that's a very obvious thing to think about. But it says if you do that, you won't get very good. I mean, you can do even better, if you use this method. Now, one point I want to note here, though, is in this 0.4% absolute error, you achieve only when there are some, tasks for which the target language has some data on which you have made some observation. May not be for this task, but some task. But what if you have never observed anything about the target language? So let's say Santhali, there is no data set anywhere. And I want to ask this question. That's possible too, but there the error bounds are a little higher, around 5 to 6%. But probably given that the whole gamut of accuracy could be as big as 20% to 100%, 5% is not that bad a gap. So now the question is how all this happens, right? And as I said, it's a regression. But what are the features that we use in this regression? There were many features that we tried. I will only tell you the things which turned out to be influential. So one of the very important features that we observed is subword overlap. So subword overlap means, so what happens in these neural systems is when you take the corpus in a language, you break each word into subwords. This is important because you can't represent all words in all the languages of the world in a single model, because the vocabulary will just explode. So you break it down to a smaller set. So typically your vocabulary is, let's say, 50,000 subwords. Within that, you want to represent all the languages of the world, or maybe 100,000 maximum, something like that. So if I have a pivot language, let's say English, and a target language where I want to estimate the accuracy, let's say Hindi, I want to measure, given an English corpus and a Hindi corpus, what is the typical overlap of the subwords? How many subwords are common? As you would guess, between English and Hindi, it will be very, very small because they use different scripts. So, but between English and German, it will be very high. The next set of features are around typological relatedness. So this goes back to the family question. So languages belonging to same family will have high subword overlap, but also will have things like they will have similar grammar, they will have similar sounds. Sometimes they will be also geographically closer. So these are some of the features that we model, and this becomes important. So how much similar the pivot and the target are to each other. Third is, of course, pre-training data size. When the original model was trained, how much corpus size was used for that, and for the target language. And the last part is that of tokenizer quality. This is a slightly technical point. So I told you that we tokenize words into subwords. We break it down. So the algorithm that does it is a statistical algorithm. It really doesn't use any linguistic information. So what happens is this algorithm does very well for languages where there are a lot of words to learn from. Whereas for languages where there are little data, the quality of the tokenizer is also bad. So it will tokenize it at wrong points, or it will tokenize it at every letter or something like that. So you don't get meaningful subwords. So with these 4 or 5 features in mind, let me present you the bird's eye view of what we learned when we did all those experiments. So what we see, so this is called a Shapley value chart. What it shows is here are the features in the columns, and in the rows are the tasks. And it shows for which task, which feature is important for prediction. Higher the value, the stronger the predictivity. Although don't don't confuse it with higher the value, it means, it's a positive correlation. It might be a negative correlation. It says how strong is the correlation, how strong is the influence. So if you look at this chart, the most important quality that comes out is the tokenizer. Like I was telling you in the previous, just before the slide, right, about tokenizer quality. So tokenizer seems to be very, very crucial. The second one is geographical distance between pivot and target. So what it means is if you are training with English, you will get very good transfer to German, because German is just next to, pretty close to English speaking country, or very good in French, but very bad in Hindi, very bad in Swahili, very bad in maybe Arabic. So the distance, smaller the distance, the better the transfer. Similarly, subword overlap has a strong impact. And again, subword overlap also has to do with language family. And sometimes, two languages which are distant might also have good subword overlap. Example is Swahili and English, because somebody asked a question about pidgin, right? So there is a lot of borrowing between languages often. So languages like Afrikaans and Swahili, they have borrowed a lot from Dutch and English and all. So that's why sometimes if you train with Dutch or English, you do get reasonable result in Swahili or Afrikaans, but you may not get that good result for Zulu, for instance, which have not borrowed that heavily on English. Yeah, so these are the important things. Now, of course, and pre-training size also matters. Now, based on this understanding, what can we do? One thing is we have to do better tokenizers for low resource languages. Now, for that, one thing I propose is instead of going with purely statistical tokenizers, which always give you better result for high resource languages and poorer results for low resource languages, can you do more, tokenizers which are more kind of fair across languages? And maybe for low resource languages, you can use linguistic rules to get better tokenizers. Then the second point is if I have a target in mind that I want to improve my performance in, let's say, Zulu, I want to choose a language as pivot, which is closer to Zulu. If I want to improve the performance in Marathi, I probably should pump in more resource in Hindi. Of course, in Marathi also, but if I can't kind of push more resource in Marathi, at least I should push more resource in Hindi. So how can you choose the pivot better? And finally, with these new ChatGPT kind of models, there is this notion of reinforcement learning with human feedback, RLHF. And there also probably we can improve low resource languages by doing RLHF with them. Now, this is a area which needs to be explored, because this came very recently and not many people have done experiments with them. But maybe there is something promising there. Now, once we understand all this, what can be a global strategy, right? I mean, there are 6,000 languages. I can't really work one language at a time. I mean, of course I can, but by that time it will be too late, because one language is dying every 2 weeks. That's the rate of language extinction. By the turn of the century, 50% of the world's languages will be gone. So we need to do something quickly. And if we can come up with a global strategy to kind of support all the languages or as many languages as possible, that will be great. So given all this that we know about transfer learning, can we chalk out a global strategy? And here are some ideas. One is, like I said, geographical distance matters a lot. And geographical distance also indirectly affects syntactic distance and subword overlap and those kind of things. So if we can cover languages by geography and pump in resources in each geography, that is very, very useful. So recently we did a study where we wanted to see how much ready we are for the next pandemic in terms of making a chatbot. So when COVID happened, a lot of people wanted to build chatbot for information dissemination, symptom checking, etc., across the languages of the world. But it was very hard to make chatbots for most of the languages. Rule-based chatbots people could make, but beyond that, it was very hard. So we did a study to show that there are big gaps across the world if you look at where we can't do anything. So red ones are places where we can't do much. So you can see whole of South Asia, there are lots of languages where we can't do anything. And English we can do, but how many people in India, for instance, understand English? Maybe 10% of the population max. So for the remaining 90%, they don't know English. Do they know Hindi, which is also a relatively high resource language? Not maybe 50%. What about the remaining 50%? Not English, no Hindi. So what language do you support? So that's why India is red, right? Similarly, this is the Niger, Congo, and Bantu languages. So this whole region is red. Eastern Africa is red. You have parts of South America is red. This part is green, by the way, because a lot of people here speak Arabic, French, or English. So they are kind of covered. So the situation geographic wise is pretty pathetic, and we can definitely do better if we systematically and strategically try to collect data. The second thing is we want to cover typology. This goes back again to the family question. So we should identify families where we don't have enough data, language families, and collect data for those. Third is one interesting thing that we can do is transliteration. So if you think of it, all the Indian languages are written in different scripts, but they share a lot of words. So a lot of Hindi words, Hindi has a lot of subword overlap with Bengali, but Bengali and Hindi are written in different scripts, so the model will never understand it. So if you transliterate Bengali to Hindi script or Hindi to Bengali script or some common script to both of them, let's say Roman script, then the subword overlap will be more apparent. So this kind of things people have tried and they help. Third thing you can also do is make region-specific LLMs. So let's say AfriBird is a bird-like model for Africa, or IndieBird or Mural. These are models for specifically for Indian languages, and they are much smaller models and actually have much better performance for these languages. So that's another strategy we should go for. And if you think of it from the Litmus studies, what we have learned is while label training data is very expensive, so has to be strategically chosen for languages. Unlabeled data and test data can also be strategically chosen. If I know the performance of a model, let's say in Telugu, it might be easier to predict, or I can probably predict with more confidence its accuracy in Kannada, but it will be much more difficult to extrapolate the Kannada accuracy from, let's say, Hindi accuracy, and even more difficult to extrapolate it from Arabic accuracy. So even there, we can strategize the data collection. The last point I want to mention in the strategy bit is that, today, when we measure accuracy across languages and we have this bunch of models, we have a table like this. Now, the question is, how do you choose a model? There are many models. You get all these accuracies across languages. Some model does better in some language, some model does better in another language. How do you choose? This is a very difficult, actually philosophical question. And what most people do is go with the average. And if you do that, in this case, you would have chosen this model called XLMR, which has the highest average. But actually, average is a very bad metric because it is heavily skewed by the highest value and the lowest value. So in fact, these problems have been studied in economics a lot under this theory of, social choice theory or the principles of distributive justice. I don't have time to get into the theory, but I will tell you the idea. The idea is, instead of average, if you look at the model which gives you the maximum value for the minimum accuracy. So if you see for XLMR, the minimum accuracy is 15.9 for Japanese. However, other models do much better in Japanese. Whereas if you look at this other model, MMT, and consider the minimum accuracy across languages for this, you get 43.1, which is much better than all others. So this method, which is called the Rawlsian choice, it asks you to choose MMT over XLMR. And you see, in terms of average, you hardly lose anything. So, and if you continuously do this in your research, that you only keep the model which is the best Rawlsian choice or a priority choice instead of the best average, over time, it will imply that you are making the minimum higher and higher and higher. So it will definitely kind of ensure a fairness across languages. So this was one of the proposal we made in a AAAI 2021 paper. Although, unfortunately, I mean, people do talk about these things, but leaderboards still, mostly look at average. Although other people are talking about other metrics on leaderboards these days a lot more. The last one thought I want to leave you with is the NLP or language technology that we are looking at today is what I call task-centric NLP. Essentially, what happens is I have a task, I have a data set for the task, and I measure accuracy and I want to make it better. But can we think of NLP as a utility-centric, technology development? What I mean by utility-centric is instead of starting with tasks like this, you want to say how the technology can help user communities. So if I make a new technology, what difference it makes in the socio-economic indices of a particular community? If it moves the needle there, that's a much better technology. I don't care if it, what's its accuracy is for a particular task and or not. And when you change the problem statement like this, everything changes. Everything changes. So then you look at language technology as an interaction between user and community and technology. And when you start measuring what is important, you would see a rule-based system can be much more useful than an LLM, in terms of those metrics. So we did an entire project we have an entire project called Ellora about it, where we are trying to enable low resource language communities by working with them. I had a couple of slides. I don't have time to cover them, but there will be my colleagues, Kalika and Sunena, and also Harshita and Kabir, who are research fellows. All of them are from Microsoft Research India. So some of them might be there already now, I don't know, but they have promised me that they will be there during the networking session, and Kabir will be there in person. Others will be on Zoom. So please ask them more about Ellora or about Litmus and everything I talked about. Thank you. And I do have time for a couple of questions, I guess.
I have one question. So in these characterizations regarding the tokenizer and the relevant features, right? Was it agnostic to the phonetic nature of the task or the semantic nature of the task? Was it like across them, or did you guys classify the tasks and then look at the features?
No, great question, actually. So we did look at, so some of the tasks are more semantic in nature, some are more syntactic in nature. And we expected to see patterns there, like what is more important and what isn't. But we did not see very strong patterns, actually. So the patterns that I showed were the ones which were most robust. If you dig deeper per task, you will see some other patterns also, but we are not very sure about their robustness. And the reason is sometimes these all also depend a lot on data sets. If you think of it, we are measuring the accuracy on only 1 or 2 data sets for that task. And based on that, we are making these comments. So that's why, that's a very good question. And there are some signals that maybe, for syntactic tasks, syntactic distance is more important and so on. But these are very weak. These signals are right now weak.
Okay, and if I can just follow up, you mentioned a point regarding Bengali and Hindi having common words and the difficulty in transliteration. So my comment, I just want to make comment that most of these scripts are phonetic in nature, right? So that shouldn't be a real issue. So I'm failing to understand the problem here. Thank you.
So that's exactly what I said. So in Bengali and Hindi, so Hindi is written using Devanagari. Devanagari Unicode characters are completely different from Hindi Unicode characters. Now your LLM will only look at your Unicode string. It doesn't understand phonetics, right? So what you can do is you can map the Hindi ka and Bengali ka to the same phoneme. Let's say same symbol, let's say K. Similarly, Hindi A and Bengali are to the same phoneme, let's say A. And if you do that, so that process is called transliteration, and that's possible because of the phonetic nature you said. You get very good results. So you are getting the right intuition.
Earlier you said that evaluation is difficult for these transfer learning models because we don't have enough label data in the target languages, right? So why can't you transfer the data back into the pivot language and then evaluate there? Like then you can probably look at the transformation for like two-sided accuracy. Like you'll have two different transformers and you need to balance that accuracy. Why is that not something that's interesting?
Yeah.
Thank you.
So how do you do that, right? You are you saying you translate, right?
Yeah. So you have a transformer that has like that can take you from the pivot to target language. Then you do the task,
right?
And then you can take it back, right? Like
I don't get it. How do you take it back? Because these are not translators, right?
No,
these are,
like so the translation is a task that's well studied. So you don't need like a universal pre-trained model.
So let's see. Back. I want to evaluate for Santhali. So I don't have any Santhali data. What are you suggesting?
So let's say that you said that evaluation, the problem is basically you have you don't have labels for the task accuracy, right? Is that correct?
So the correct thing is, I mean, what I mean is, so I can't evaluate in Santhali. I might be able to train a Santhali sentiment analyzer using transfer from English. But I cannot test it for its accuracy in Santhali as long as I don't have any sentiment data in Santhali and annotated by Santhali speakers.
But the same tasks you have evaluated it on English, right? And you would know what the answer for that is in English.
Right. So, but English accuracy is high, I already know. English accuracy doesn't help me estimate Santhali accuracy.
Maybe I'm phrasing this wrong. So I'm saying like, you don't need to train, you don't need like all the tasks to be trained. You just need like a certain, you need basically translation task ensure that your sentiment analysis is accurate, right?
Yeah. So I understood your question. So you are talking of something called translate test. That's actually something which people try. In fact, the mega benchmark work that I talked about was that, right? So if you have Santhali data, I mean, let's say if you have English sentiment data, you translate it into Santhali and now give it to the model and see the accuracy. You could do the reverse also. Take the Santhali annotated data, don't train even a model for Santhali, translate it to English and run the English model. So people do all these combinations. Now, there are two major problems with these approaches. The first problem is all tasks are not translatable. Sentiment is a translatable task to some extent, but let's say parts of speech tagging is not a translatable task. And the other problem is translation engines don't work for low resource languages. You don't have translation engines for them, which are good enough. So even they don't give you good estimates.
So even the basic tasks, there's a problem.
Yeah. So you can apply this method for French and English, for Spanish and English. But why should we try that? Because we already, have good models for French. I mean, have data sets for French and Spanish. But we don't have data for, let's say, Zulu. We don't have data for Konkani. Now, there, the translators are also pretty bad. You can't rely on them.
Okay. Thank you.